Hey everyone, Paulo here. So let's just jump right in. De-aging. That's uh, that's the skinny here. I don't know what is or will be possible in the future, but let's see what Ars Technica has to say about it. So a lot of these stories, I just want to start off with. Um, a lot of these stories I think are more hopeful than they are real, right? So they're trying to convey the hopes of researchers, I think. And so let's see what they have to say here. Could getting rid of old cells turn back the clock on aging? So I'm not an expert in biology, but I'm sure Amber Dance isn't either. And let's see, researchers are investigating medicines that selectively kill decrepit cells. So, okay. So that sounds interesting enough. I don't know. I guess we're going to find out what they have to say about it. James Kirkland started his career in 1982 as a geriatrician treating aging patients. I've never heard that word before. Geriatric medicine, I guess. Okay. But he found himself dissatisfied with what he could offer them. Okay. I got tired of prescribing wheelchairs, walkers, and incontinence devices, recalls Kirkland, now at the Mayo Clinic in Rochester, Minnesota. He knew that aging is considered the biggest risk factor for chronic illness, but he was frustrated by his inability to do anything about it. So Kirkland went back to school to learn the skills he'd need to tackle aging head on, earning a PhD in biochemistry at the University of Toronto. Today, he and his colleague Tamara Chiconia, yikes, sorry, a molecular biologist at the Mayo Clinic, are leaders in a growing movement to halt chronic disease by protecting brains and bodies from the biological fallout of aging. So, right, so anti-aging medicine. All right, so this new generation of anti-aging medicine specialists. If these researchers are successful, they'll have no shortage of customers. Yeah, people are living longer, and the number of Americans aged 65 and older is expected to double to 80 million by 2040. Don't think about it. Don't think about it. No, I won't be quite that old yet. While researchers like Kirkland don't expect to extend lifespan, okay, they hope to lengthen health span, the time that a person lives free of disease. Okay. One of the targets is decrepit cells that build up in tissue as people age. These senescent cells have reached a point, due to damage, stress, or just time, when they stop dividing but don't die. Okay. While senescent cells typically make up only a small fraction of the overall cell population, they accounted for up to 36% of cells in some organs in aging mice, one study showed. And they don't just sit there quietly. Senescent cells can release a slew of compounds that create a toxic, inflamed environment that primes tissues for chronic illness. Senescent cells have been linked to diabetes, stroke, osteoporosis, and several other conditions of aging. These noxious cells, along with the idea that getting rid of them could mitigate chronic illness and the discomforts of aging, are getting serious attention. The U.S. National Institute of Health is investing $125 million in a new research effort called SenNet that aims to identify and map senescent cells in the human body as well as in mice over the natural lifespan. And the National Institute on Aging has put up more than $3 million over 4 years for the Translational Geroscience Network multi-center team led by Kirkland that is running preliminary clinical trials of potential anti-aging treatments. Drugs that kill senescent cells, called senolytics, are among the top candidates. Small-scale trials of these are already underway in people with conditions including Alzheimer's, osteoporosis, and kidney disease. It's an emerging and incredibly exciting and maybe even game-changing area, says John Varga, chief of rheumatology at the University of Michigan Medical School in Ann Arbor, who isn't part of the TGN, the Translational Neuroscience Network. But he and others sound a note of caution as well, and some scientists think the field's potential has been overblown. There's a lot of hype, said Varga. I do have, I would say, a very healthy skepticism, he warns. He warns his patients of the many unknowns and tells them that trying senolytic supplementation on their own could be dangerous, right? And so this is one of the huge problems of medicine, right? The human body is insanely complex, and we know so very little. So here's some little thing that we know, that these senescent cells cause these problems, and they increase in number over time. And so the goal here is just to remove those cells and see what happens, right? So the hope is that the negatives of those cells, the positives of removing them would make up for any of the problems of those cells being there, or something along those lines, right? So it's interesting. I don't know if in the end it'll do much, right? So that's one of the big problems with medicine, is we get an idea, like, here's this one particular thing that happens with aging. What happens if we reverse that one particular thing, or clean up that one particular thing? And it might have other very serious negative effects, because we just don't know. Researchers are still untangling the biology of senescent cells, not only in aging animals, but in younger ones too, even in embryos, where the aging out of certain cells is crucial for proper development. So far, evidence that destroying the senescent cells helps to improve health span mostly comes from laboratory mice, which, okay. Only a couple of preliminary human trials have been completed, with hints of promise but far from blockbuster results. Right. Because we're a lot more complex and a lot bigger than mice, right? So, yeah. Even so, Kirkland and Chiconia speculate that senolytics might eventually help not only with aging, but also with conditions suffered by younger people due to injury or medical treatments such as chemotherapy. There may be applications all over the place. And that's the thing, right? Is there's all these different efforts going on in the anti-aging market, I would assume. And likely a lot of them will have different various uses. All right, so good cells gone bad. Biologists first noticed senescence when they began growing cells in laboratory dishes more than 60 years ago. After about 50 cycles of cells first growing, then dividing, the rate of cell division slows and ultimately ceases. When cells reach the state of senescence, they grow larger and start exhibiting a variety of genetic abnormalities. They also accumulate extra lysosomes, bag-like organelles that destroy cellular waste. Scientists have found a handy way to identify many senescent cells by using stains that turn blue in the presence of lysosome enzyme called galactosidase. Jeez, I'm really bad at these types of words. That's often overactive in these cells. Scientists have also discovered hundreds of genes that senescent cells activate to shut down the cell's replication cycle, change their biology, and block natural self-destruct mechanisms. Some of these genes produce a suite of immune molecules, growth factors, and other compounds. The fact that specific genes consistently turn on in senescent cells indicates that there may be more to senescence than just cells running out of steam. It suggests that senescence is a cellular program that evolved for some purpose in healthy bodies. Hints at that purpose have emerged from studies of creatures far earlier in their lifespans, even before birth, right? So this is a thing, right? Likely this biological function serves some purpose, and just eliminating cells, that have reached this point might have bad effects. Cell biologist Bill Keyes was working on senescence in embryos back in the early 2000s when he stained healthy mouse and chick embryos to look for beta galactosidase. Galactosidase. Little blue spots lit up in certain tissues. He soon met up with Manuel Serrano, a cell biologist at the Institute for Research in Biomedicine in Barcelona, who noticed the same thing. Cells with signs of senescence turned up in the developing brain, ear, and limbs, Keyes and Serrano reported in 2013. Keyes, now at the Institute of Genetics and Molecular and Cellular... Why are there so many N's? Ands. Cellular Biology in Strasbourg, France, focused on mouse and chick embryonic limbs, where a thread of temporary tissue forms across the future toe tips. Unlike most embryonic cells, the cells in this thread tissue disappear before the animal is born. They release chemicals that help the limb develop, and once their work is done, they die. At a molecular level, they look a lot like senescent cells. Ooh. Serrano, meanwhile, looked at cells in an organ that exists only in embryos, a temporary kidney called the mesonephros that forms near the heart. Once the final kidney develops, the mesonephros disappears. Here too, beta galactosidase and other compounds linked to senescence appeared in mouse embryos. See, so even if senescent cells are bad, it might be that so I think what they're saying here is that these cells are similar to other types of cells that are very useful. And so therefore, just killing cells that look like senescent cells might be bad. The cells in these temporary tissues probably disappear because they are senescent. Okay, so here they're even saying they look senescent because they are. Probably. Certain compounds made by senescent cells call out to the immune system to come and destroy the cells once the work is done. Okay. Scientists think the short-term but crucial jobs these cells perform could be the reason senescence evolved in the first place. Right. Other studies suggest that senescent cells may also promote health in adult animals. Judith Campisi, a cell biologist at the Buck Institute of Research on Aging in Novato, California, and others have found senescent cells in adult mice where they participate in wound healing. Connective tissues called fibroblasts fill in the wound, but if they stick around, they can form abnormal scar tissue. During normal wound healing, they turn senescent, releasing compounds that both promote repair of the tissue and call immune cells to come in and destroy them. In other words, the emergence of senescent cells in aging people isn't necessarily a problem in and of itself. The problem seems to be that they hang around for too long. Serrano suspects this happens because the immune system in aging individuals isn't up to the task of eliminating them all. And when senescent cells stay put, the cocktail of molecules they produce and the ongoing immune response can damage surrounding tissues. Okay, so it sounds more like it's an immune system problem than a senescent cell problem. But, you know, this is one article written probably not by an expert in all this, and we can only learn from what they understood. This person who likely has a degree in journalism, Amber Dance. All right. Senescence can also contribute to cancer. As Campisi has described in the annual review of physiology, but the relationship is multifaceted. Senescence itself is a great defense against cancer. Cells that don't divide don't form tumors. On the other hand, the molecules senescent cells emit can create an inflamed cancer-promoting environment. So senescent cells arise near a cell that's on its way to becoming cancerous and might alter the locale enough to push that neighbor cell over the edge. In fact, Campisi reported in 2001 that injecting mice with senescent cells made tumors grow bigger faster. Were these already tumorous mice? the fact that these cells make tumors grow bigger faster is one thing, but that doesn't prove that senescent cells themselves can push the cell over the edge into becoming cancerous, right? So you got to be careful with some of this stuff. If senescent cells in an aging body are bad, removing them should be good. To test this idea, Darren Baker, a molecular cell biologist at Mayo Clinic, devised a way to kill senescent cells in mice. Baker genetically engineered mice so that when their cells turn senescent, those cells become susceptible to a certain drug. Okay. The researchers began injecting the drug twice a week once the mice turned 1 year old. That's about middle age for a lab mouse. Okay. Treated mice maintained healthier kidney, heart, muscle, and fat tissue compared with untreated mice. And though they were still susceptible to cancer, tumors appeared later in life. The researchers reported in studies in 2011 and 2016, the rodents also lived on average for 5 or 6 months longer, which if 1 year is half their age, I mean, that's a 25% increase. That's pretty good. These results generated plenty of interest. Baker recalls and set senescence biology on the path toward clinical research. That was a boom. A new era for cellular senescence, says Viviana Perez, former program officer for the SENNET consortium at the National Institute of Aging. Baker followed up with a study of mice that had been genetically modified to develop characteristics of Alzheimer's. Getting rid of senescent cells staved off the buildup of toxic proteins in the brain, he reported, and seemed to help the mice to retain mental acuity, while as measured by their ability to remember a new smell. Of course, geriatricians can't go about genetically engineering retirees, so Kirkland, Ciconia, and colleagues went hunting for senolytic drugs that would kill senescent cells while leaving their healthy neighbors untouched. They reasoned that since senescent cells appeared to be resistant to a process called apoptosis, or programmed cell death, medicines that unblock that process might have senolytic properties. Senolytic properties. Does that mean killing of senescence? Is that what they mean by senolytic properties? Some cancer drugs do this, and the researchers included several of these in a screen of 46 compounds they tested on senescent cells grown in lab dishes. The study turned up two major winners. One was the cancer drug dasatinib B, an inhibitor of several natural enzymes that appears to make it possible for the senescent cells to self-destruct. The other was quercetin, a natural antioxidant that's responsible for the bitter flavor of apple peels that also inhibit several cellular enzymes. Each drug worked best on senescent cells from different tissues. The scientists found, so they decided to use them both in combo called D plus Q in studies with mice. In one study, Ciconia and Kirkland gave D plus Q to 20-month-old mice and found that the combination improved the rodents' walking speed and endurance in lab tests, as well as their grip strength. And treating 2-year-old mice, the equivalent of a 75 to 90-year-old human, with D plus Q every week, extended their remaining lifespan by about 36%, compared to mice that didn't receive senolytics. The research reported in 2018. Ciconia, Kirkland, and Baker all hold patents related to treating diseases by eliminating senescent cells. To the clinic. Scientists have since discovered several other medications with senolytic effects, though D plus Q remains a favorite pairing. Further studies from several research groups reported that senolytics appear to protect mice against a variety of conditions of aging, including the metabolic dysfunction associated with obesity, vascular problems associated with atherosclerosis, and bone loss akin to osteoporosis. That's a big deal, collectively, says Laura Niedernhofer, a biochemist at the University of Minnesota Medical School in Minneapolis, who's a collaborator on some of these studies and a member of the TGN Clinical Trials collaboration. It would be a shame not to test them in humans. A few small human trials have been completed. The first, published in 2019, addressed idiopathic pulmonary fibrosis, a fatal condition in which the lungs fill up with thick scar tissue that interferes with breathing. It is most common in people 60 or older, and there's no cure. In a small pilot study, Kirkland, Chiconia, and collaborators administered D plus Q to 14 people with the condition 3 times a week for 3 weeks. They reported notable improvements in the ability of participants to stand up from a chair and to walk for 6 minutes, but the study had significant caveats. In addition to its small size and short duration, there was no control group, and every participant knew they'd received D plus Q. Moreover, the patient's lung function didn't improve, nor did their frailty or overall health. Right, so they really didn't prove anything, right? I mean, it was hardly a study at all. Sounds like it was hardly even a study. Niedernhofer, who wasn't involved with the trial, calls the results a soft landing. There seemed to be something there, but no major benefits emerged. She said she would have been more impressed with the results if the treatment had reduced the scarring in the lungs. Yeah. The TGN is now running several small trials for conditions related to aging and other diseases too. Kirkland thinks that senescence may even be behind conditions that affect young people, such as osteoarthritis due to knee injury and frailty in childhood cancer survivors. Okay. Right, so here's a bunch of stuff that's happening. D plus Q and some other drugs. D plus Q and F, whatever Fistian is. Chiconia and Kirkland are also investigating how space radiation affects indicators of senescence in the blood and urine of astronauts, in conjunction with 2 companies, SpaceX and Axiom Space. They have hypothesized that participants in future long-term missions to Mars might have to monitor their bodies for senescence or pack senolytics to stave off accelerated cellular aging caused by extended exposure to radiation, which is a really interesting, different topic, the radiation in space. And that basically what you get exposed to in that type of environment. Kirkland is also collaborating with researchers who are investigating the use of senolytics to expand the pool of available transplant organs. Despite desperate need, about 24,000 organs from older donors are left out of the system every year because of the rate of rejection is higher for these than younger organs, say Stefan Tullius, chief of transplant surgery at Brigham and Women's Hospital in Boston. In heart transplant experiments with mice, he reported that pre-treating older donor mice with D plus Q before transplant into younger recipients resulted in the donor organs working as well or slightly better than hearts from younger donors. Or slightly better. Okay. That was huge, says Tullius. He hopes to be doing clinical trials in people within 3 years. Okay. I mean, we need clinical trials, right? So, I mean, that's the whole point of doing the study on mice and then doing it on people is we get a sense of what might be possible, and then we try it on people, and we usually find that it's just not as effective in people because humans are a lot more complex, right? There's a lot more cells in a person than a mouse. It takes a lot more of a drug to get really distributed amongst the human body than it does for a mouse. So there's just a lot of things that are different. But mice they live quick lives, and it's easy to do long-term studies on them. Healthy skepticism. Numerous medical companies have jumped on the anti-sentience bandwagon, notes Paul Robbins, molecular biologist at the University of Minnesota Medical School. But results have been mixed. One frontrunner, Unity Biotechnology of South San Francisco, California, dropped a top program in 2020 after its senolytic medication failed to reduce pain in patients with knee osteoarthritis. So there's a lot of these links to other stuff, and I wish there was like a little bit more information about that, like without having to go read this. Like why? How long was it going? Was it something that was a long going? Was there not immediate results? I'm curious about what constitutes a failure. I think we just don't know enough about the right drug, the right delivery, and the right patient, the right biomarker, says the University of Michigan's Varga, who is not involved with Unity. More recently, however, the company reported progress on slowing diabetic macular edema, a form of swelling in the back of the eye due to high blood sugar. Despite the excitement, senolytic research remains in preliminary stages. Even if the data from TGN's initial small trials look good, they won't be conclusive, says network members Robbins, who nonetheless thinks positive results would be a big deal. Success in small study would suggest it's worth investigating in larger studies and in the development of drugs that are more potent or specific for senescent cells. And I'm imagining that, well, yeah, I don't know, because I don't think drugs generally get dispersed through the whole body. I mean, yeah, they enter the bloodstream, and in theory, they go everywhere, but how much do you actually need, and where does it actually get delivered? Like, there's a lot of problems with... I mean, I guess you just inject in multiple locations, or you... I mean, I don't know, right? I'm not an expert in medicine. I'm urging extreme caution, says Campisi, who is herself a co-founder of Unity and holds several patents related to anti-senescent treatments. She's optimistic about the potential for research on aging to improve health, but worries that moving senolytics quickly into human trials, as some groups are doing, could set the whole field back. And so I think this kind of idea keeps kind of coming up, where it's like, in the 70s there was lots of advancements in AI, but we lacked the computing power to do anything with it. And so there was a winter in AI research, I think is what they kind of call it, like just a winter. And so we see all these little things here in biology, and we just don't know enough. And so we move quickly and we hope for results, and the results aren't there. And so I think that's what she's afraid of, is that it's going to create a funding winter until maybe our understanding of biology catches up with some of this stuff, and then we're able to more effectively implement or use this stuff in the future. That's what happened with gene therapy in the 90s when an experimental treatment killed a study volunteer. I hope they don't kill anyone. Seriously, she said. Yeah, right. And gene therapy is still not huge today, right? I mean, there are some gene therapies that are more successful now, but it's still not huge. Side effects are an ongoing concern. For example, Dasantin B in D plus Q has a host of side effects ranging from nosebleeds to fainting to paralysis. Yeah, undoubtedly. But Kirkland thinks that may not be an insurmountable problem. He notes that these side effects show up only in cancer patients taking the drug regularly for months at a time, whereas anti-senescence treatments might not need to be taken so often. Might not. Once every 2 or 3 months might be enough to keep the population of senescent cells under control. Might. Another way to reduce the risks would be to make the drugs that target senescent cells on specific tissues. And I think that's ultimately right what you have to do, because there's so many different tissue types, and there's so many tissues, and it's all over. I mean, the human body is big. Niedernhofer and Robbins note that the annual review of pharmacology and toxicology, for example, if a person has senescent cells in their heart, they could take a medicine that targets only those cells, leaving any other senescent cells in the body, which might be doing some good alone. For the strategy to work, though, doctors would need better ways to map senescent cells in living people while identifying such biomarkers. Such biomarkers is a major goal for SENNET. Campisi suspects it will be hard to find good ones. It's not a simple problem, she says. A lot of basic and clinical research must happen first. But if everything goes right, senolytics might someday be part of a personalized medicine plan. The right drugs at the right time could help keep aging bodies healthy and nimble. It may be a long shot, but to many researchers, the possibility of nixing walkers and wheelchairs from many patients makes it worth taking. Right, okay. So here's a little bit about Amber, contributing writer at Knowledgeable Magazine. I call into question. I suspect they're woke, but who knows. Looks forward to a long, healthy, and retirement punctuated by... Okay, so here she is promoting it. I don't know why. I don't know why. That's really weird. Okay. So this was, I guess, just reprinted in Ars Technica. Biology is complex, right? I don't know. A lot of this stuff is so silly and really isn't going to go the way we suspect it will. And I think that we just don't know enough about biology. What we need is to be able to represent biology as a mathematical model. And if we get to that point, that's where we're going to see massive, massive gains, like rapid gains in understanding and rapid gains in being able to create medicines. Right now, it's all shots in the dark, right? It's like, oh, here's this one type of thing. And if we could just treat that one type of thing, which we really aren't very good at doing, which is why cancer medicines, for the most part, cancer medicines kill all the cells in an area, not just the cancerous cells, right? That's like you're injecting poison for the most part, hoping that you kill the cancer before you kill the patient, and then the patient can recover. So, that's a lot of this stuff. We just don't know enough, right? Our understanding of medicine is in the dark ages still. I mean, it's certainly better than it was 100 years ago, but it's slowly coming around. And I would just highly recommend caution before you go thinking that a lot of today's ailments will be magically cured by science. It's too complex, and it's just too big a field, and we don't know enough yet, and we don't have the right models for it yet. But it's not to say that it's not worth studying. I think it is, and we certainly need people who are very interested in going out and getting the models created that will ultimately allow us to do these things. So cool. It's an interesting story. They're trying to get you excited for it. I don't really approve of this lady, especially that ending where she's like looking forward to using this stuff in the future. Maybe it's good, maybe it's bad. It's good to learn about things that they're doing in medicine, and and to have an understanding of what might be possible in the future. Anyways, this is Paulo. Thank you for joining me. If you liked what you saw, please like, comment, subscribe below. If whatever I can do to make this better, just let me know. And I hope you all have a great day.